Oops. Okay, so I guess we can get started. So first of all, I'd like to thank the organizers for the opportunity to speak, as well as for this very wonderful workshop. So today, I'll talk about tail effect in binary scattering. This is based on the work with the fantastic collaboration with Zvi Bern, Julio Palau-Martinez, Badu Roiben, Michael Ruf, Michael Salom, and Mao Zheng. So to begin, I'd like to remind the audience that we need to push the precision frontier of gravity because of need from current and future experiments. So even with just the very first event from LIGO, they're able to constrain the deviation from GR much better than the previous results from pulsars. And in the next 5 to 10 years, we will have the second and third generations of gravitational wave detectors. And with these third generation detectors, we will be able to see hundreds of thousands of events with a sensitivity to 6 post-Newtonian order, which is a perturbation theory in the inspiral phase. So because of this tremendous power of experiments, we need to advance our theoretical understanding of the binary system to an unprecedented precision level. So what's the status of our current understanding? So in the inspiral phase, you can do the usual post-Newtonian expansion, expand both Gn over R and velocity v squared because of Virew's theorem. Or in the case of scattering or the hyperbolic orbit, you can expand Gn over R by orders in velocity. So in this plot, each horizontal row corresponds to a fixed order in G, and each vertical column corresponds to a fixed order in the post-Newtonian expansion. So this 0 pm will be a Newtonian potential, 1 pm will be a famous Einstein infield Hoffman potential. And over the past few years, we have tremendous progress from the collective effort of the community. So now we already have some partial results at 6 post-Newtonian orders. And in the case of scattering for order G cube, recently we have the complete result for G cube scattering. And earlier this year, with my collaborators, we have the potential contribution to order G to the fourth on scattering. So the obvious goal of this talk is to complete the conservative dynamics at order G to the fourth. So now let me just review some basic ingredients in the binary dynamics. So the first few orders, they're dominated by the so-called potential region. So for a binary system with velocity v, momentum transfer q, the potential graviton or the so-called potential mole, they have the energy and stream momentum scale as the following. So the energy is suppressed compared to the momentum by small velocity. So the graviton propagators are of shell, and we can expand the energy to the numerators, and they turn into the time derivatives. So say differently, the time propagation effect of potential gravitons is can be treated as the tidal expansion of local time derivatives. And therefore, these interactions are effectively instantaneous, and that's the usual Newtonian-like potential. So in the field theory or amplitude language, because these gravitons, they're of shell, so the 2-to-2 scattering, they enjoy the elastic unitarity. So the amplitudes are given by a phase shifts, as we learned from quantum mechanics. And these phase shifts in the classical limit reduce to the classical action or the radial action. So combining these two, you can see that this dictates the iterative structure in the 2-to-2 scattering amplitudes. And for optical theorem, we know that the imaginary part of an amplitude comes from this type of iteration. So say differently, these potential gravitons, they're of shell, and therefore their propagators are purely real. So the only imaginary part comes from intermediate onshore matter. So once you remove this iteration, the remaining classical part is manifestly real, as it should be, And also it corresponds to the radial action in classical mechanics. So this is the amplitude action relation that we used earlier this year, which is a hybrid combination of the earlier EFT approach from Neil Rothstein, Chung Rothstein alone, and the Aikana approximation dated all the way back to ACV in the 90s. But obviously, the LIGO detectors, they see the physical gravitational waves, so we need the onshore gravitons. And these are given by the so-called radiation graviton, or the radiation mode, where the energy and the momentum have the same scaling. And therefore, the propagators can go on shell, and the choice of boundary conditions is important. So for instance, if you have the Feynman I epsilon, then the propagator, this single graviton propagator has the principal value and the I pi delta function. So these two possible effects, one is that we have the dissipation, since these on-shell physical gravitons can carry away energy and angular momentum. And this is the so-called radiation reaction started at 2.5 pn level at level of equations of motion. Another interesting effect is that if you have multiple radiation graviton, they can give you a time symmetry effect that is still conservative, but these onshore graviton, they still leave non-trivial feature, say non-local in time action. Because you need more gravitons, so these effects are higher order for post-Newtonian level. But as you can see that all these effects, 2.5 or 4 pn, they're all within the reach of current and future detectors. And therefore, we need to study that. And also from a theoretical point of view, it's also more interesting to study this radiation, because this is what makes GR like interesting theory than some Newtonian-like system. So using these two different modes, now we can summarize the binary dynamics into the conservative sector and the dissipative sector. So in the conservative sector, we have the contribution from only potential gravitons. This will give you an instantaneous Hamiltonian, starting at 0 pn, or in the scattering, linear in G. But we also have conservative effect from the so-called tail contribution coming from time symmetric radiation. This will give rise to non-local in time action, started with 2 or more gravitons at force post-Newtonian level, or G to the force in scattering. We could also have the dissipation coming from either single or more radiation gravitons, which will lead to linear in the radiation reaction or nonlinear order. So the nonlinear order will be the 5 pn or G to the force that Thibault talked about earlier. So now let me focus on the order G cube for the scattering. So for order G cube, the even in velocity part is given by only from potential region. But the new feature at order G cube is that we first have the effect coming from radiation. This R in velocity part is the linear radiation reaction. And now it has been computed by several different methods from the Aikana approach, the KMOC formalism, and the linear response. So this real radiation reaction comes from the interference of the radiation graviton, which has an imaginary part in the propagator. And this can interfere with the onshore matter, which gives another imaginary part. So together, they become real and are in velocity, given by a diagram like this. And you can also get this very elegantly from the linear response formula in the recent paper by Damore. So the dynamics becomes more intricate when you go to order G to a force. So for this even in velocity expansion, on top of the usual conservative potential, we also have the conservative tail. But also starting at 5 pn order, we also have the radiation reaction square as mentioned in Damore's talk. But the tail effect, they have a very distinctive feature, which is that it will produce will produce the log in velocity. And similar to the older GQ, we will also have a R in velocity part, which is coming from linear in the radiation reaction. So now let me focus on the tail effect. And for this tail effect, we have a lot of guidance from the traditional post-Newtonian community, as well as the EFT framework. So in the EFT language, as explained in Damo's talk, that this comes from the emission from a quadrupole moment. So we have this red line, which is the radiation. It back scatter with this potential in the far zone, and then this radiation come back to another quadrupole moment. So in the field theory, we have the corresponding Feynman-like diagram with these two being radiation. And the first feature of the tail effect is that it has a UV divergence. So you can think about this UV divergence coming from this one-loop correction to this quadrupole moment. And because this UV divergence on the coefficient has to be proportional to the original quadrupole moment. And if you work out the prefactor, it's proportional to the energy times the square of the quadrupole moment, which is the energy loss. And therefore, this coefficient has to be proportional to the energy loss in scattering. And in the case of scattering, we expect this one of the epsilon divergence will cancel after we add all the regions, the region including only potential. However, this radiation, it has a special feature that it has the V square in the ultra-dimensional part. So after you add all the regions and cancel the divergence, this divergence will still leave a non-trivial log in the final answer. And in the case of shell action, you don't have the explicit velocity, but instead you have the energy from this quadrupole moment over the mu, the RG scale, and this will give rise to a similar log in the omega over nu. And this non-analytic log, after you do Fourier transform to the time domain, this will give a non-local in-time action. So that's the story about the divergence. However, the tail part, they also have the finite contribution. And this is place where the boundary condition is important. And in this work, we use the Feynman I epsilon for radiation propagators and then take the real part in the end. So at order G to a force, this matches the principal value prescription, which is the definition of conservative tail effect. And as we learned from this paper, also matches the prescription in this paper by Bini, Damo, and Girolico. So after we have this physical picture about tail effect, now we can promote this to the on-shell unitarity cuts. Since we need two radiations, so we have two 5-point amplitudes. And these two radiations, they combine into this Compton amplitude. And you can refine this, unitarity cuts. So you can place additional cut to separate the two matters into this type of diagram, which only contribute to the tail effect. And this diagram that contribute to both potential and the tail. And for this type of cuts, as you can see, they have gravitons start and off on the same particle. So therefore, these are the cuts that only contribute to the tail region. So after these unitarity cuts, you can merge them into an integrand by standard approach. And then for the integration, we will construct the integration by parts identities and differential equations as before. And needless to say, they're very powerful. And even with this tail region, we can still use 1 meter line cut per loop since we expect this coming from the soft region or the wall line formalisms. So since we have two different modes now, we have to discuss what are the regions that we do for this integration. So we have 3 loop momenta. They can be either the potential or the radiation region. So we have these following combinations. So the first one is purely potential, which we have computed before, and this is strictly conservative. We have the region with one radiation, and these are the one correspond to the linear radiation reaction, which is dissipative. And in this talk, we want to focus on the tail effect, which is coming from the region with two radiations. But this region also includes the nonlinear radiation reaction, which is dissipative. But we can project this out by imposing the principal value prescription, as I mentioned earlier. And finally, there's a region with only radiation, but this region is not sensitive to the momentum transfer, and therefore they're purely scaleless and no contribution at all. So in the end, we find agreement among different methods, from differential equations, self-integration, and non-relativistic integration. And one non-trivial check is that since we expect the tail only comes at this order, so we won't have any iteration. So even though from the diagrams, we do have iteration, but in the end of the day, after integration, they all vanish. So this is a consistent track of our result. So now just to remind you the result we got earlier this year. This is the amplitude with only potential region contribution. So after you factor out all these mass factors, so the non-trivial part of the amplitude can be described by this simple function. And this nu is the reduced mass ratio. So the first term corresponds to the test particle or the probe limit, which takes a very simple form. And the non-trivial information comes from this first order cell force, the linear in nu part. And for this potential only result, we have the divergence coming from this tail effect, and also some finite part that contains the elliptic functions or the way to polylogs. So after adding this conservative tail effect, we have the full result with the same prefactor. And the divergence, the probe limit, they remain to be the same because it has no tail contribution. And after adding the tail and the pure potential region, this one of the epsilon divergence cancels. But as I explained earlier, this leaves a non-trivial log in velocity part. And in the potential region, we have, once we expand in velocity, we have pi squared contribution. And this remains to be the same after adding this new tail effect. But it has a non-trivial modification to the finite part. And the result is still written in terms of the previous elliptic functions, as well as the way to polylogs. So just one comment on the structure. So because tail only appears at this order, so we expect no change, and as we verify explicitly, that the iteration is the same as before. And since we're dealing with amplitudes, one feature is that we have simple mass scalings. And since the conservative amplitude directly mapped to the radial action, so this simple mass scaling propagates to the full conservative angle. So in this amplitude, we only have the only linear in nu part, or the so-called 1SF. So these propagate to the radial action and the corresponding angle. And we have a lot of help from the traditional post-Newtonian or the classical GR approach. So as we finish our result almost a year now, so for this work in June by Delpa, Kailin, Liu, and Porter, they use classical approach and verify our result orders in velocity. And in this paper by Bini, Dameo, Giralico, they calculated this very non-trivial tail contribution, and they give the 4pn, 5pn, and 6pn results. And after taking our results and expand in velocity, we find perfect agreement for the overlapping sector, and we give the higher orders in velocity. So thanks to the very non-trivial, tremendous effort in the traditional PN community, we can verify our result and find perfect agreement. And this also agree with another independent work from Blumlein, Meyer, Marquardt, and Schaeffer through the first order cell force result. So another interesting part is to compare our result with numerical relativity. So this is the plots we got from Mohamed Cahill, Sandra Buono, Jan Steinhoff, and Justin Weiss, where they took our 4P G12 force scattering and compare with the scattering in numerical relativity. So in this plot, the horizontal axis is the impact parameter over the Schwarzschild radius, and the y-axis is the scattering angle. So here, this around 90 means that this is a right turn. It's actually not a small angle scattering at all. But as you can see that our G12 force analytic result actually agrees with numerical relativity very well. And as we go from large to small impact parameter, the deflection angle becomes larger and larger, but we still improves better from the previous these G lower order in G results. And these authors, they can take this direct analytic result and improve by the effective one body, which include the order, the test body result, and check with the deviation from numerical relativity. And as you can see, this orange line is a G12 force after EOB process result, agree with the numerical relativity very well, and the deviation is about only a few %, even for small impact parameters. So let me finally wrap up. So using techniques from scattering amplitudes and effective field theory, we have completed the conservative scattering dynamics at order G12 force. And we find perfect agreement with the classical approach. And for the future, one definite thing is we want to complete the full dynamics to include the dissipative effect. And for this part, we have the linear in radiation reaction, which will be R in velocity. And as I mentioned, at order GQ, this has been computed using the KMOC formalism, Icona approximation, or linear response. So this should be straightforward to calculate in the future. We also heard from Damour about this nonlinear in radiation reaction, which will be even in velocity. And it will be interesting to find out how to complete this. But the path to higher order, especially for this tail effect, looks clear now. And another very interesting aspect is now we have the conservative dynamics for scattering, and how do we apply to bond orbits? And we also have a very recent paper from Porter's group discussing this aspect. And I'll stop here. Thank you very much.
Thank you very much. So now we have time for 5 minutes for the discussion. Before we start, I actually would like to tell Peter Marker that if you want to send me the PDF of your presentation by email, I could try then to share the screen, okay?
I sent it.
Okay, I didn't know because I'm not looking at the emails. Okay, thank you. So let's try to take questions. I see a hand up from Rafael Porto.
Hi, Cheshire, nice talk. I'm confused. Are you saying the memory is 0?
Sorry, what do you mean?
The memory contribution from 3Soft, right? The memory that Peter will talk about in a second, the memory that gives you QQQ corrections to the conservative sector. You say it's a 0, it's scaleless, does not contribute.
So, well, okay, so.
But it is of order G5, not G4.
Exactly.
But there is in principle a G4 contribution. It's in the EFT calculation.
I don't think so.
Yeah, of course. There is there in Ricardo and Stefano's calculation. Is there also in Blumlein et al. There is an angular momentum, for example, already at G4. But you're saying something more interesting. You say that 3 soft is scaleless.
No, 3 radiation is scaleless.
3 soft, right? That's what you mean by 3 radiation, no?
Okay, if that's what your definition of soft, then yes.
Sorry. Yeah, okay, yes, 3 radiation.
So ultra soft, yeah.
Yeah, ultra soft, good. So you will say that this will give 0 contribution from memory to the 4 p.m. That would be your answer.
Okay, I think what I mean by 3 is ultra soft and what you mean is slightly different. Yeah, so here, when I say 3 ultra soft, I mean that literally all the loop momentums are ultra soft and they're trivially 0. I think we can all agree with that because they're just scaleless. And when you say 3 ultra soft, I think what you meant is this one.
That one be radiation, exactly.
Right. Yes, I would say it's 0.
So then you disagree.
Not in the conservative sector.
Exactly. So then you will disagree with the calculation of the EFT.
So there could be a mismatch in the translation, but in terms of the final scattering angle, we have the complete conservative answer.
Sorry, but you have the new scaling that maps also Thibault's calculation, the Max, Marquardt, and Blumlein et al. That
exactly.
Is coming from the tail. But there is a memory contribution, a QQL, a QQQ, that contributes a nu square that makes this fail, that makes this mass scaling fail, so they claim Blumlein et al. That you will disagree with, right?
Good. So for this, so for this nu square contribution, so that's partly what I want to emphasize here is that for the conservative part, we only have 1 SF, not just for first few PM orders, but orders in V. It's only 1 SF.
Sorry, but you can do the 1/gamma trick now, get the radial action and get all the new factors, right?
Exactly. So that's why it's only 1 SF.
Yeah, but that should include the nu square conservative to all orders, and you will be missing the memory.
No, so what we're saying is that there's no nu square for the conservative sector.
Exactly. You will say that the memory should vanish in the conservative sector.
Exactly. Yes.
Which is not consistent with the calculation, if I understood correctly what Blumlein et al. Are saying, it's not consistent with that result.
Yes.
Okay, so you disagree with that. I just want to make sure I understood.
Okay, good, yes.
Okay, because I would have thought that 3 radiations will contribute here. We find a non-zero value, and that's why we are struggling with the memory piece of the conservative part. So you're saying it's not there.
It's not there.
And it's not obviously not there just because you symmetrized it. And then you will basically do retarded plus advanced, you get the opposite sign, you just kill it. Maybe you just kill it by hand and it should have been there.
No, we just follow the book and it's not there.
Okay, so Rafael, sorry. Can we actually...
I stop.
We only have 5 minutes. If we have
I stop. Thanks, Chashen. That was very nice. Thank you.
Okay.
Thank you, Rafael.
Let's take a few more comments or questions from other people. Ricardo, you wrote something on the chat. I don't know if you want to say something.
Oh, yes, if there is time. Well, it's not only not consistent with our result, but it's not consistent with the Moore and colleagues checks, no? Because they show that to make vanish the nu square contribution at G4, you need the contribution to the memory. Just that the contribution you need is not what we have computed, and it's not what...
Yes, so that's what I mean, that there could be a mismatch in the translation, but in terms of scattering angle, there's no nu square contribution for the conservative sector.
Yes, but then since it's not, the memory must provide a missing contribution to make it vanish, the nu square contribution to G4.
Sorry, could you repeat that again?
Yes, at G4 you don't have nu square contribution.
Yes.
So since with the memory you do have a nu square contribution, well, not you, but it was checked in this Bini Geralico D'Amour, then there
so
must be a memory contribution.
Bini D'Amour, they don't have new square. They only have 1SF. Bini D'Amour Geralico, they only have 1SF. In this conservative sector.
It was just
okay.
If you put together the AFT, you want to cancel, the cancellation of the new square can only happen if there is a non-zero contribution.
He's talking about the angle here.
So the EFT, it could be canceled after you add up different contributions.
It's the same.
Yeah, so in Bini D'Amour Geralico, they have their local and non-local. Each of them has like 2 SF results. But when we add up like the final result, like the one I show you, like equation 6.20 in their paper, it's only 1 SF.
Okay, so maybe this discussion can continue later. Thank you very much, Shanshan, for the presentation.
Thank you very much.